It's hammers number 2.
All right, how's it going? Not too bad. All right. Who is still having trouble with Eclipse and Window Builder? I know you are. Anybody else? So I found a procedure you can use on the Collaboratorium PCs to install Eclipse and install Java and install Window Builder, and it works. And I posted it on Canvas in the top under General Information. It's the last item on there. And it's a really annoying bug if you just go through the straight installation of Eclipse. It tells you have to install Java. You install Java, you have to install Window Builder and Swing, and then when you try to go to your design window, you get the following error. So basically it checks the version of Java that Eclipse is using and compares it to the version that Window Builder is expecting. And if Eclipse is using a version that's earlier than the one Window Builder wants, it gives you an error. So here's the error that's popping up. Eclipse is version 0. Please upgrade. And it refuses to run Window Builder.
Oh yeah.
And this is an established bug. It's on the list of bug reports. So what's going on here?
I remember that being something like, I had that on my desktop last week where my desktop had version 10, but in Eclipse I was building things with 1.8. And that was the reason, that was the error it was giving me.
Okay.
And I had
was it saying Eclipse is 0?
Yeah, I installed 1.8.
So whoever wrote this decided they were just going to pick up the last digit of the version number, apparently. Because, you know, 1.7 is version 7 and 1.8 is version 8 and 1.10 is version 0.
Doesn't that why they skipped 9 Windows?
Yeah.
Maybe, is it?
It's
My understanding was they wanted 10 to be like
It was the 10th
the
version
final.
of Windows.
Yeah.
So they just wanted to call it 10
Yeah.
or something. I don't know.
Well, it's supposed to do with like some of their coding. So it's like, oh, Windows 95 is registered as like Windows 9.
Yeah. So this is a bug, and if you go to the Eclipse website, it's on the list of known bugs, and the resolution says if anybody wants to patch this, please let us know, because they say they have no active Window Builders developers anymore. I don't know if that's still the case, but so I'm ditching all of this next year. It doesn't help you this year, but we'll probably do IntelliJ next year, because Eclipse just doesn't feel like it's being maintained well enough to go in a classroom. But a fix for this is to install Java version 8, not 9. And so I posted it on Canvas, and it definitely works in the Collaboratorium. And after you download the files, you can throw them on a flash drive, and you don't have to download. Download's the longest part of the process. But that lets you at least work with Window Builder in the Collaboratorium, because the software version we have on there right now is also broken. And that's my fault, because I didn't actually check Eclipse to see if it worked. I just said we still want Eclipse on here for spring, but I should have actually checked it. So that doesn't help you next year, but it'll help everyone else. All right, so if Eclipse isn't working for you and you want to use it in the Collaboratorium, the version on the PCs does not work as is, go to Canvas, follow those steps, and you can install it yourself. And it works, including Window Builder. So I confirmed that this morning. Yeah. Yeah, it's giving weird errors too that look like installation issues. All right, so any questions? All right, what I'd like to do is take a look at, way back in PA2, take a look at a different version of PA2 that uses TreeMaps. I don't believe we've done this yet. And I want to go through this just because it's a nice example of this idea of taking an object and just treating it as a thing, right? And this object might be a string, or it might be some big, huge thing with all kinds of mechanisms inside and variables and data and things like that, but it's still just an object, right? And we want to be comfortable with the idea of treating an object as just this thing. And if we want a linked list of these, we don't have to really think too hard about how to make a linked list of these objects. It's really just a linked list where our node's data type is whatever type this object is. And it's almost completely irrelevant whether that object is something simple like a string or something huge and complex like a binary tree whose nodes contain hash tables, whose keys are strings and whose data values are tries or something like that, right? So it's this idea of being able to look at this piece of your code and not necessarily get tricked into following down logically what each of these individual pieces actually is. So in that spirit, I coded up a version of the WordList assignment, so Pt1. And it's 28 lines of code, including 1 line of comment and a few imports. And this is the whole Pt1. It's not broken down into those classes where you call the class and it constructs, but the functional behavior of Pt1 is captured in these few lines of code. And it's because we're taking advantage of these available classes called TreeMap and ArrayList. Okay, so a TreeMap is like a hash. Okay, so what's a hash? A hash is a set of pairs of keys and values. If you have a hash, you can go into the hash with a key and it will give you back a value associated with that key. And if the value is not stored in there, it gives you a null or something, right? So it's an extended version of an array. An array is something you can go in with an integer from 0 up to the last index, and it gives you back whatever data is associated with that index. A hash is a more general version. We can go in with any key, could be an integer, could be a string, could be something weird, and it'll give us back a value. So an associative array is the way we've described this also. And a tree map, so hashes and maps, kind of interchangeable terms. A tree map, a tree hash is a hash that we can also request things in sorted order. So there's a tree structure built into this hash so that we can say, give me the first key in my hash, give me the second key, give me the third key, and so on. Because normally, if you just have a set of keys and values associated with them, there's no sort of inherent ordering to these keys. Now we could pull all of them out and alphabetize them and see what the first one is, but a normal hash has no notion of that. A tree map does. So tree maps have this extra stuff. Back when I used to have an internet connection. So a tree map, it's an extension of an abstract map. It's got keys and values, but it has methods like first key, which returns the lowest key according to whatever ordering is defined for the type of key. And then it has higher key, which you give it a key and it gives you the next key right after that in that same ordering. And as with most of these things, this is a generic. Okay, it takes two parameters, K and V, which tell you what type of keys you have and what type of values. So if you want a hash that's keyed by strings and the data values are also strings, you can do that. If you want it keyed by integers and the data values are doubles, you can do that. Okay, it's all the same class, but when you construct it, you specify what's the type of the keys, what's the type of the values, and it creates the class based on that. So what do we do here? This is all boilerplate. There's some imports, there's a class definition, there's our public static void main. We set up our scanner as usual. So we're going to be reading from standard in. And then here's where the good stuff happens down here at line 10. The first set of good stuff. at line 10, we say let's construct a tree map. So the type of the key is a string. And the type of the value is an array list. And it's not just an array list, it's an array list bracket integer. And what's that about? Why is there a bracket integer after that?
It also takes the generic.
Because it's also generic. We have to specify E, which is the type of data that we're storing in our array list. Array lists are like linked lists. They look like arrays, but they're actually linked lists too. So here we're saying we want to construct a tree map, a hash that can be sorted, where the key is a string and the value associated with a key is a linked list of integers. That's our position list. So the key is a string, that's the word we're trying to index, and the value associated with it is an array list of integers. That's our position list. So this one structure, this tree map, is able to hold our entire collection of data that we're trying to build for our index. For every word that we get from standard in, we're going to use that as a key, and the value associated with it is going to be a linked list of positions where that word occurred. Right? And that was what we stored in our word list in PA2. So that sets up a tree map. We're calling it WordList, no coincidence. And we construct it as new tree map, and you have to specify those types of parameters again in the constructor. No arguments to the constructor, just paren. So that creates our empty word list. And we still need a counter to know what word we're looking at from input. So we initialize current position to 0. Every time we read a word, we're just going to increment that. And we'll use that to know when we see this word, this was the 7th word in the input, so we'll store a 7 in its position list. And then this is the whole main loop. This is what actually builds your word list. And it's several lines of code. So while sc.hasNext, sc is a scanner, so while there's more words to read from standard in, we say sc.next, that gives us the next word, we convert to lowercase and we store it in Word. Right, this is probably identical in function to something you had in PA2 somewhere. And then these 3 lines do the following. So WordList is a tree map. Tree maps have a contains key method. Contains key tells you whether or not this string is a key in your hash. So this says if my hash does not contain a key that matches my word, well, what does that mean? It means this is the first time we've seen this word. So we do a put operation on our hash, and put takes 2 arguments. It takes a key and it takes a value. And we're saying add the following to my hash. Add a key of word and associate the value to be a new array list. It's an empty list. So if we get a word and we haven't seen it before, we go ahead, we put it in our word list hash, and we associate an empty linked list with it. But if we get a word and we have seen it before, we don't do anything yet. Okay, so this 3 lines of code, this if statement, is only for the first time we see a word. But now when we get down here to line 18, we know for sure that the word is in our hash map. Because it was either there to begin with or we just inserted it. And we know that its value is a linked list that contains all the positions, not including this one. And so in either case, all we got to do is add our current position to the end of that linked list. And this one line does that. So WordList is our hash map. Get is a method which takes a key, gives us a value. We give it the key of our word, it will give us back a linked list. Linked lists have an add method. Add methods take an argument, which is the integer you want to add, and the behavior is to add that to the end of the linked list. So this one line does all of that, and it creates your new entry in the hash map. And so we just keep looping. We pull in a word, add it to the hash if it's not found, and then do this blue line to store the position, and we do that until hasNext returns false, we close the file and we're done. We've built our word list. So this is effectively your build index routine. And I didn't put the print method into a separate routine the way you were supposed to in PA2. I just went ahead and printed it here. So how do we print? WordList is a hash map. It has a first key method. It returns a key, which is a string. That's alphabetically the first word in our map. Okay, so that's the first one we want to print out. And we do a while loop. If that key is null, we're done. Otherwise, we print out the key, followed by a colon, and then I'm just concatenating the linked list. So wordlist.getKey returns the array list associated with that, and I'm just concatenating it. And array lists have a built-in toString method. And it basically prints a comma-separated list of the data in your linked list with brackets around it. And then we just set key equal to the next higher key, and we go back to the top of our while loop. And that's it. So if we were to run this just on itself, for no particular reason, so we can type in all of that code as input, and so there's the output it produces. So that's alphabetized, and there's a list of all the occurrences, all the positions. So obviously I didn't let you do this, right, for PA2. And it would be a good exercise in terms of getting familiar with TreeMaps and ArrayLists and things like that, right? But it would miss the low-level development of those data structures. But I want you to see it, and I want you to think about it, and I want you to, in general, unless you're told specifically, don't do this with a class that's already defined, right? In general, you can start to think more and more about how do I reuse what's already available, right? So that if you need to do this outside of the classroom, you don't have to go back and reinvent the wheel, right? Or all the wheels that we need to make this work, right? And if we wanted to have a linked list of these word lists where we're reading different input files and we want to store them in a big linked list, right? Well, we've got a way to create a word list. We bundle that into a class, and then we could just make an array list, angle bracket word list, and we're good to go, right? This is where you really get into the power of like code reuse and modularization and things like that, because you can build in all kinds of amazing functionality into a class, and you can pick it up and you can just say like, okay, now I want to take these things and access them off of people's names. And you can just make a hash map, and for each name associate one of these, whatever this type of object is, and stuff like that. So this is why object-oriented programming has become sort of a kind of de facto standard. It's the way that things have gone, because it really kind of encourages this this idea of building something and then other people can use it and put things on top of that. When you go out and you buy a piece of hardware, like that brain scanner that somebody was working with for their SLP, right? It usually comes with an API, which is often a Java class. And you can, or you know, the I/O we're doing in these labs on the Raspberry Pi, right? The whole GPIO, general purpose I/O system, is just a big class. And when you use the factory and you create an instance of it and you get this GPIO object, it's got all the mechanisms inside to condition a pin for input or output and put in a pull-up resistor and read the state of it and things like that. And if you don't use those, that's fine. But it's just an object. You can pass it to a method, you can pass it to another thread or whatever, right? So this is a really powerful programming model. And we're deep inside it, even if we're not always taking advantage of it. So I just want you to think about that. We'll come back and play with regular expressions next week and see another example of this.
Can you put that on your repository or whatever?
Yeah. Watch the video and type really fast.
Yeah, I was gonna say, you know what's better than watching a video? Copy.
Do you fully appreciate the science that we've got these days?
I do. walls extend.
All right, I'll call it WordList. That should be up there.
So notes for your example of PA4
Mm-hmm.
for Monday, you only had like one class.
Mm-hmm.
Is that what we're doing, or because shouldn't you have like a tree class? And
You need a tree class.
Tree node?
Yeah. Did I actually like?
It just had one like a main.
Oh, that was. I think that was pseudocode.
Oh, okay.
I think I was sort of saying like what the top level gameplay is, which is
Oh,
read the
okay.
tree and then play a game, update the tree if you're incorrect and rewrite it and then go back. But yeah, you're gonna want a tree class. We'll do some tree code in a little bit. You're gonna want a tree class, and you may want some other. You're gonna have a lot of methods, definitely. Tree class may be the only other class you need though. But as usual, right, it's kind of totally up to you, because some of it depends on your preferred coding style. Well, questions?
Is a TreeMap a standard data structure, or is that just a Java?
A tree map?
Yeah.
Well, I don't know what standard means really, but it's not one of the usual ones we talk about in a first or second data structure course, I don't think. But
I guess
it's
how
standard in Java.
Yeah. So I guess like how difficult would that be to implement something with identical features in a different language?
I haven't really thought about it. So making a hash is pretty straightforward. Making a tree is pretty straightforward. So how do you put these together? Maybe while you're building your hash and adding keys to it, you're just also building a binary tree in parallel. And then when you want to pull out your first key, you just go into your tree and you traverse all the way to the left. Right? So you do a left node right traversal, and first key just returns the first key that it finds in there. So I don't think it's has to be more complex than that. It probably is because of efficiency, but it could just be two structures, a binary tree with keys and then a hash of keys and values, and you just keep them in sync. But I'm pretty sure what they probably do is they somehow augment the keys in here to actually build the tree into the hash itself, which would be cool.
Can you look at the code or no?
I think so. I've never looked for the source code for this stuff, but as far as I know, it's all out there. And if not, there's an open version of the JDK, so you could find it there. Yeah, it would be fun to dig into.
Mm-hmm. The tree maps, this one specifically.
Yeah. All right, well let's do some tree code. There's nothing really mysterious about it, and I don't think you're going to have problems with it. But let's just code up some tree operations in Java, just so that we can say we've done it. And probably after the break, we'll do red-black trees, and that's a topic that really needs a good 45 minutes solid concentration to get nice and confused. So we'll probably do that after the break. But let's code up a tree. We may as well call it tree. And we need nodes in our tree. So we're going to have a second class. And I'm just going to call it tNode. And let's just do a binary search tree. You can modify this for your decision tree. Okay, but let's just do a binary search tree since we're used to that, and I don't want to give away code that you're going to write. So what would a tNode look like? Let's say this is a tree of integers.
Data, and then you have two leaf nodes, which is like tNode, left, tNode, right.
Good. And that may be all we need in our T node. We could put in some constructors to initialize and such, but that's possibly all we need. So what about our class tree? What do we need in here? What should we call it?
Handle.
Handle? Root?
Root.
Should we do handle or root?
Stem.
Stem.
Root.
We'll put handle in the comment. Because it is a handle to the tree. Alright, so T node is a root. Root is a T node. And we may as well initialize that to null, right? Because we don't have sentinels in.
So I know that naming doesn't necessarily matter all the time.
Mm-hmm.
In like a professional setting or whatever, if you didn't call it handle, would it be kind of common courtesy to like comment it as handle?
I don't even know if handle is a thing anymore. It was a thing when I was learning this. And it may be a dated term, but I don't actually know if there's an official term for the thing you use to grab hold of a linked list. So and if we don't have a sentinel node, right, we need something. So I've been calling that handle. But for a tree, pretty much everybody's going to use the term root for the root node. Other than the fact that if there is no root, it's kind of weird to talk about the root. Right, it's like talking about the cow you don't own. This is my cow who I don't own because she doesn't exist. Right, it's a little weird. So handle might be more technically correct. But if you're at a company where those things make a difference, you'll probably figure that out pretty quickly. Or you could post it on Stack Exchange and see what people say. But it's a good question. I just don't have a solid answer for it.
Do like a Twitter poll.
Yeah. All right, so the root of the tree is going to be initially null because we never do sentinels with trees. Do we need a constructor for our tree? I mean, do we need to write a constructor for our tree?
I don't think so.
Probably not. I mean, the only thing a constructor might do is set the root to null. But if we set it to null up here when we declare a root, that's as good. So it's not even clear what a constructor would do, so let's not do one for now, at least, if we need one. Can you write?
You can write a class. How did I not know that? You can write a class with no constructor.
Yeah, there's a default constructor.
Oh, okay.
Yeah. It's not obvious that there should be, but it turns out there is. So what else do we want to do in trees? Anything?
We better do something.
Better do something.
Add node.
Okay, let's do an add node. So let's add something to our tree. So what would this look like?
You said we're storing a number, yeah.
We're storing an integer.
If root is null, root equals new node.
Should we make a temp variable?
Yeah. Let's start off with that. And let's go ahead and throw a constructor in here so we don't have to constantly construct a node and then set the data equal to n and set the left and right equal to null. So this dot data equals data, left equals right equals null. That a good constructor? Looks good to me. Don't have to say this dot left, this dot right, because there's no ambiguity, right? But if we call this data, we got to say this dot data to mean this data. If we call this dat, we can just say data equals dat. No ambiguity. All right, so this creates a new node whose data value is n, whose left and right children are null. If the root is null, root equals temp, return. We're done. So what if the root's not null? There's a couple of answers here.
Compare n to root.data.
Can this throw an exception?
If root.data is null.
Should
root.data.
We have to put in, if we're only editing data with the, if we're using the constructor to change the data field,
Then no,
then we should never have
Yeah.
null in there.
So the only thing that could cause an exception here is if root is null and you're checking that up here. So this should be fine. So if n is bigger than root.data, what should we do?
It should go to the right child. So.
And then do what?
So
Do the
temp
same thing.
root dot right equals temp.
Okay, so move to the right and do the same thing. That's one option. Moving to the left will happen if n's less than the root.data. So whatever we do here, we're going to do again on the other side.
What is equal to?
We can assume it's not equal to, or we can just let whatever happens happen. But we should handle that, right? We should either insist that you don't insert the same value twice, and if we insist that, we should check in the beginning to make sure it's not found in there.
I mean, if you add and these are all in if statements, it would just run through and it would meet none of those conditions, and
Right.
they would just do nothing.
Yeah, yeah.
Recursion,
Hey, there you go.
do,
That's what I'm doing.
add to the right. Do,
So how do we do that?
root dot right dot add.
I like it.
Yeah.
Timeframe.
Yeah.
That looks good.
Return.
But
Root dot right is a T node,
mhm.
and those, we haven't put an add method number.
Okay. So it's a little more complicated. Right, root.right is a T node.
Instead of checking root, can we have a different variable that points to the root of whatever subtree we're looking at? And
Mhm.
change that each time we go through the,
Yeah, so that would be a iterative
okay.
version. We could have a temp pointer and move down.
But could we change it every time we then, or right before we call the function again to make it recursive?
I think so.
Are we,
think
Wait, you
that
said the
would work.
problem is root.right is a T node,
are we able to
and
extend
root is a T
T-node?
node?
It, basically the add function doesn't belong to right.
Right.
Can you extend T-node?
We could, or we could just write the add function in T node.
Sure.
Could we also make right and left trees?
We could. So that would be another way to do it. Right? We could make everything a tree instead of a T node.
But then that's making.
But somehow, wherever we have this stuff, we've got to have our add method in there.
I mean, like still have the T node, but the left and right are trees that have their own T node root. I don't know if that's like spaghetti-like, but
It's spaghetti-like. It might work. Okay, so I saw some of this on PA3, or sorry, on PA2, with people's word lists, where you had a position list, but your nodes were actually little position lists that weren't being used as position lists. They were just being used for a few data fields in there. And that works, but I think a cleaner way is to have an add method in here,
And where?
inside the tNode class.
And then you, okay.
Instead of the tree.
Or in
Or-
addition
oh,
to.
okay.
But your add method in your tree is really just going to call root.add. So it's really just kind of a wrapper. So we can code that up in a second, but we got one more thing we got to think about, which is this is potentially going to change the root in some subnode, but it's not really linking things up.
Yeah, didn't our algorithm in 222 have, we returned a root?
We returned a root, right? So we probably want to do that again. And we want to return a tNode. And so in this case, we could set root to temp, but really we just need to return temp. And down here, root.write.add is going to return a tree which looks like the right subtree but has this new node added to it. And what do we want to do with that new tree that we've created? We had this tree and we've traversed down to this point and we decided, okay, our data is somewhere in this triangle. So we call this thing's add method, and now somewhere in here this number n gets added. And it returns to us the root of this tree. If we don't do anything, the right child of this node is still that original triangle.
You do root.write equals root.write.add n.
Exactly. So let's write some code. Let's see if this actually works. All right, you do the rest. So what's our tNode class? It's got integer data, I'm just going to set those to null right here. I'm not going to bother giving that a value.
Public tNode and data.
All right, so there's our handy constructor. And let's do an add method. So this will add a node to the tree with this root. So let's see. So if n is bigger than this node's data, we want to insert to the right. So right.add n. Why didn't it like add? let's see. Getting tangled up. It's been a while. So we're going to have a T node, which is the root of a tree, and we're going to have to check to see if right's null, but that's a side step. So if we want to insert to the right,
So if it's not static and it's an instance method, so maybe it's because they're magnitude null. So like if right's null, can you call add?
so say it again.
If right is null, are you able to call?
No, we're gonna have to take care of this still. Right, but I'm not sure why it's unhappy about this. Oh, because I'm not returning yet. Okay, so but I'm wondering, do we have to actually return a T node?
You just say return, right?
I'm not sure we need to return.
You can just say void until you think that you found a spot to return.
I mean, if it's an instance, you don't need to, right?
Let's try this and see if we get into trouble. So if n's bigger than the data we want to insert to the right, if there's nothing on the right, we're just going to set the right to a new T node, okay, with the given data value, and then we're done. Right, we can just return. Otherwise, there is something to the right. So we can just say add that node to the right, to the tree whose root is the right node. I think that will work.
Shouldn't you make right equals new T node n?
Yes. Thank you. Okay, otherwise we'll insert on the left. So if left is null, left equals new T node n, return, otherwise left dot add n. So that's our first stab at an add method. I honestly don't know if it's going to work or not. We're going to find out. We're going to debug it, but doesn't. So this is an add method for a T node. Right? If you have a node, you can say, this is the root of a tree, go ahead and add my node to the tree that's rooted right here. Okay. Our tree class also wants an add method. So here's the root of the tree. I don't think we have to return anything. All right, so our add method says if the root is null, just make a new T node, set the root equal to that, we're done. Otherwise, call the add method on the root, and then we're done. What do you think? So the add method is part of the node, right? And it's doing the things it's supposed to do. And in the tree class, we have a particular node in mind which we call the root. That's the root of the tree. And when we say add something to the tree, it either modifies the root or it uses the root's add method to actually add something into the tree that's not null. So let's do a quick traverse and then take a break, and then we'll try this. So let's do a left node right traversal. Claim that's our left node right traversal algorithm. So if the left is not null, call left node right on the left subtree, and then print out the data itself, and then if right is not null, call left node right on the right subtree. And again, this is the T node traversal method. So you're going in with a T node. We're going to say T node dot left node right. It's going to do a traversal from that point where that T node is the root of a tree, right? It's going to traverse the left subtree, print the root, traverse the right subtree. So the version we're going to call from our client code, let me call this uppercase. Looks like this. So if the root's null, there's nothing to do to traverse it, but if the root's not null, call left node right on the root node. Look reasonable? Heck, let's just try it. Fair enough. Let's see what it does. We got 5, 12, negative 11, 1, and 5. We got negative 11, 1, 5, 5, and 12. Yeah, I put 5 in twice. I don't know why I did that. Let's do it like that. All right, there's your sorted data. So we did good. Yay. All right, so this is a little awkward feeling maybe compared to C, because when we try to make this object oriented, right, there's the tree itself and then there's the nodes. And in C, we were forcing you to sort of pull back a pointer to a root and then cobble that together to build the tree from the pieces that you're updating. And we kind of like skirt all of that in here, right? We really just sort of have a tree node, and we say if we want to add to the right, just go ahead and call the add method on the right subtree. And the only exception is when there is no right child, and then we just explicitly set the right child to that new single node. And we could say tree.root.add to get to these methods without having an add method in the tree class, but in the idea of information hiding, right? We don't want the user to have to come in and interact with the root of the tree. We'd kind of like the root to be private. In fact, we could go ahead and mark it private if we wanted. But then we just make an add method and a traverse method inside the tree class that the user can get to, and they just call the method on the root, except when the root's null. All right, so kick that around, let's take a break, let's come back at 1 o'clock, and if there's no questions on this, we'll go ahead and do red-black trees. I'm gonna put some stuff on the board while you're out there so I don't have to write it while you're here.